Hello, for Physics Lab 3 we were asked to find the mass of a black hole given its location and also given multiple x and y positions of a star orbiting the hole and also given that star's mass. In this lab, the star is our system and we are studying its motion in the interacting object with this system whose presence is the main cause of the system's motion, or in other words, the black hole. The main result of this lab was that the mass of the black hole is equal to about 6.072 times 10 to the 31st kilograms. The accuracy of this mass was confirmed with WebSign, which is the website where we were given the data to solve this problem. Though this mass value is important, it does not tell us anything about the physics involved in calculating it. So let's first talk about our lab by explaining the fundamental principles behind it. The first principle is the momentum principle, which states that the final momentum being equal to mass times velocity, is equal to the initial momentum plus the net force times the change in time, delta t. From this principle, the equation F net is equal to the derivative of momentum with respect to time can be derived. For this problem that we were given, we had to approximate this value right here by using specific time intervals, delta t, and momentum data over those intervals. And from this, we got the equation delta p over delta t. F net can be split into two components, F net parallel and F net perpendicular, which moves and F net parallel moves parallel to the motion of the system, which is the star, and F net perpendicular moves perpendicular to the motion of the star. Our next principle is Newton's second law, which states that force is equal to mass times acceleration. From this law, this equation right here, which is Newton's law of universal gravitation, can be derived. And this law relates the mass of two objects and the distance between them to the magnitude of the force between them. And g, which is the universal gravitational constant, is equal to this quantity here. And now to our computer model. The most important part of our code is right here. And that's where F net parallel, and F net perpendicular are found. And they were found using the changes in momentum, right here, over each time step, which was delta t was equal to 86,400 seconds, or 1 day. And then in order to find the mass, which was the main objective of the lab, we just plugged the radius, which we found here, into the universal law of gravitation. However, I noticed later that I just used the x coordinates and the y coordinates that were given to me, but I did not compare them to the black hole's position, which doesn't really make sense because the star is orbiting the black hole. It's not just orbiting the origin 0, 0, 0. So I made another model to incorporate this. In this model, as you can see, I compared the radius, or I found the radius by using the x minus 0 because the x component of the black hole was 0, and then actually this is the position of the black hole. And the y component was 3 times 10 to the 10th power, and so I compared the y components that we were given to this component in order to find the radius. And I will elaborate on the difference between these two models later. But here is what our model looks like. And as you can see, the arrows start off really, really small, and then they're going to gradually get much, much bigger. The reason the size of the vectors grows so drastically at the end is because the star is much closer to the black hole than it was at the beginning of the model, and the gravitational force between them is much stronger. Actually, I analyzed this by looking at the point where the net force was greatest, which is the second point here. As you can see, the distance magnitude from the black hole is about 10 times smaller than the distance of magnitude from the black hole at the beginning of the model, and thus the net force for this point where the magnitude is small, or the magnitude of the distance is smaller, is much greater than it was for the first point. And this point right here is just the last position of the star. And also, if you look back at the model, you can see that the F-net parallel and is going, even though it's going parallel to the motion of the star, it is going opposite to the motion of the star, while before it was going with the motion of the star. And that's because at first the star was moving towards the black hole and now is starting to move away from the black hole. So the forces between the black hole and the star are now going against the star's motion. Now back to the discussion of my two different models. Here's the data I obtained from the first model, which is incorrect, and the second model, which is the one I believe is correct. Oddly, the mass average for the first model, which is right here, is closer to the correct WebAssign value than that of the second model. However, I believe WebAssign had a correct mass range rather than one mass value, and thus we cannot really compare these masses to the true mass of the black hole. We can look at the standard deviation of the data for the two different models, though. The standard deviation of the first model, or the incorrect model, is about 10 times larger than that of the second model, which is the one I believe is correct. And since there really shouldn't be no variation in the mass of the black hole to begin with, this value of the standard deviation proves that this is the more accurate model. Now to questions. First, what does it mean? In your analysis, you should discuss how F-net perpendicular, F-net parallel, and F-net are different from delta P delta T over delta T perpendicular, delta P over delta T parallel, and delta P over delta T. In this problem, we set all the forces to their corresponding delta P over delta T values. However, it should be noted that it is the net force, or all of these net forces, that cause all of these changes in momentum. So even though they have the same value in this problem, they represent two very different things. Next question, what if? Imagine the black hole whose mass you found was removed and a different black hole was placed in the same location. Assume the motion of the observed star remains unchanged and is affected only by the gravitational force of the new black hole. Could you tell the difference? Actually, I really believe that you cannot tell the difference because you were only given certain data in this problem, and that was the location of the black hole, the mass of the original star, and then the positions of the star. And so if none of this information changes, you can't do anything else to the problem. And so this would mean that the mass of the black hole would stay the same as it did throughout this problem. And that is the end of my lab.